Okay, so we're going to take a bit of a deeper dive into covalent bonds, looking at some categories of covalent bonds, but it's been a little bit. Before we start, establish what we know about covalent bonds. So for each of these statements, we just want to circle one answer. So first thing, covalent bonds form between atoms of what type of element? Everything that you are working with today is going to be with nonmetals exclusively, looking at the right side of the periodic table. As a result, these elements have either similar or different electronegativity. We have a definition for electronegativity here. It's ability for an atom that is part of a covalent bond to attract electrons towards itself. So maybe you don't remember this, maybe it's been a little bit, but because they are nonmetals, similar part of the periodic table, it's reasonable for us to think that they are going to be similar in electronegativity. Now, similar does not mean exactly the same, and we'll look at those differences there. But for the most part, they are closer to each other than to metals in their electronegativity. So as a result, similar ability to attract electrons, covalent bonds are going to involve the sharing of the valence electrons in bonds. So, seen this before, baseline definitions talking about covalent bonds. And so here is where things are going to get a little more involved, but not too much. So, just mentioned that term electronegativity. We have that term here. It is important. And the thing to realize is electronegativity increases. Atoms get better at pulling electrons towards themselves. And that's what we should think about. When we see higher electronegativities, those are atoms that are good at attracting electrons. When you see low electronegativities, you see things that are bad at pulling electrons to themselves. So we're going to look at some trends. We've seen these before, but it's probably been a while. How things change going down the table and how things change as we go across. So general trends in electronegativity. And I've got a web page pulled up here. Not that. That is the screen cast thing. Here we go. All right. So looking at this, you can see, and it may be cut off a little bit on the left side, but the more yellow something is looking, the lower the electronegativity. The more orange and especially red things look, the higher the electronegativity. And as we go down a column, and you can see down a good example, looking at group 17 or group 7 halogens, you can see generally going down this column, fluorine at 3.98, chlorine 3.16, 2.96, 2.66. As we go down a column or a group of the table, the values tend to decrease. And we can generally assume that this is true. So going down the table, we can assume that electronegativity is also going to decrease. Things get worse at taking electrons from other things as we go down the table. Opposite, however, is going to be true going across. And if you look at the second period, so lithium, beryllium, boron, this is the best example of that. You can see it just gets progressively darker and darker. The values keep increasing until we get to fluorine. Fluorine is really, really good at taking electrons from things. Neon, however, not so much, which is interesting because it's in the same column and it's even further over to the right than fluorine is. However, the whole goal for any of the elements in here, they want to have those 8 valence electrons, the octet rule. Well, everything in the noble gases already have an octet. So they don't need any additional valence electrons. And so as a result, you can see that for the most part, they don't even have values. They really don't attract electrons to themselves. Now, krypton, xenon can form covalent compounds with certain other elements, but they are pretty rare, so we don't want to think about them too much. So, take a moment. We're going to pause the video real quick. Below, there are 10 pairs of elements. So all you want to do is look through each pair of elements, and based on what we just saw, the general trends in electronegativity, which of the two should have a higher overall electronegativity value. So take a moment. problem for this, pause the video, see how this goes. So hopefully when we did this, you saw the following as having the higher of the two electronegativity values. And if you look at this, there are some common elements. You notice things in the halogen column, things like bromine, fluorine, chlorine, and kind of near there towards the top of the table on the right, oxygen and nitrogen as well. So we'll look at those a little more in depth pretty soon. But going down, just want to make a quick point. There are two pairs of elements in here that would form an ionic bond. In the top row, you have sodium and oxygen. So remember, sodium is a metal. Same thing with potassium and bromine. And the thing to realize with this, for ionic bonds, we are looking at the largest general difference in electronegativity. And we can see that on the periodic table here. And it's a little bit tough to see. I need to set this down so I can scroll this over. But, well, there we go. So looking at potassium, a little hard to read the number, but it has a 0.82 value. Sodium is a 0.93. Get rid of that. Over on the other side, oxygen, 3.44, bromine, 2.96. So the biggest differences that you're going to notice are in ionic bonds. But our focus for today is covalent bonds, so we are going to continue on to that. So, all the pairs that we saw beyond those two, beyond the sodium and oxygen, beyond the potassium and bromine, would form covalent bonds. And what we are looking at specifically is that not all the elements, even if they're not metals, are as good of shares of those electrons. Some things are just better at taking electrons. And so we want to categorize these as what are the best, what are the high electronegativity elements, and what are the low electronegativity. So our high electronegativity, this is what we saw up there. So nitrogen, oxygen, fluorine, so in that second row, and then down chlorine, bromine, and iodine. These are what we consider our high electronegativity elements. All the other nonmetals, things like carbon or hydrogen or phosphorus or sulfur or whatever else, they're only okay. They're better at taking electrons than the metals, but they're not as good as that high electronegativity group. So what this means that in a covalent bond, even though one atom may not have full domain over both electrons in that bond, they may not be pulled, they may not be directly in the middle. They might get pulled to one side or the other. So we have over here 5 pairs of atoms, and all of these are considered to form a polar bond, or a polar covalent bond. So take a moment, read over the definition that is here, and then try to circle the element that is most likely to pull the electrons towards itself. And this is what's going to be the higher electronegativity. So pause the video for a sec and see what you get. So hopefully we had those 5 circled, and you can see each of the elements that's there is in that high electronegativity group. The nitrogen, oxygen, fluorine, chlorine, bromine, iodine, these are the ones that are better at pulling electrons towards themselves. And that's what happens in this. When we define something as a polar covalent bond, it means that we are going to get some uneven, I know this seems kind of silly, but uneven sharing of the electrons that are there. They just happen to get pulled towards the element that is higher electronegativity. What this means, too, is that in that bond, because those electrons are being pulled to one side, we can expect a partial negative charge on the more highly electronegative atom. And in the absence of that, a slightly more positive charge on the one that is low. And we can see this. We got another little simulation to look at. So looking at atom A and atom B, atom A has a low electronegativity, and you can see surrounding it that it's kind of blue. And our electrostatic potential, that's just saying is it positive or negatively charged. You see that positive charge on the left side on A. For B, we're going to scale this up to being a bit more electronegative, and as a result, you can see on the more electronegative atom, there's this negative charge that surrounds this. So in the event that we have two atoms that are very different in their electronegativity in a polar covalent bond, you can expect a positive end and a negative end. The electrons are still being shared, just not as equally as they could be. So finishing this up, the opposite situation. So something else, if they're not different, then it's entirely possible that they are kind of the same. So the opposite situation, when we have two atoms that are just as good or about as good at taking electrons as the other. So each of the pairs of elements below have similar electronegativities. And in some cases, they're the same atom. That makes it very easy to see. So when they're the same or when they're similar, if they're both in the low category or both in the high category, there is going to be a bit more even a distribution of the electrons there. So covalent bonds that form between elements that are considered to be, between elements, these are considered to be nonpolar, or that there's no difference or a slight difference. So in these cases, we would not expect there to be a very big difference. And in the case carbon and carbon, hydrogen and hydrogen, fluorine and fluorine, even though carbon and hydrogen are on the lower end, fluorine's on the higher end, the fact that these are things bonding to the same element, there's not going to be any difference in the pull of the electrons one direction or the other. Carbon and hydrogen, even though they're on different sides of the table, they're still pretty similar. Same thing, bromine and iodine, they're pretty close to each other. They should have similar electronegativity. So again, when we talk polarity, polarity implies difference. We're going to have relatively equal or even sharing in the case of elements that have similar electronegativity. So this is where you have the chance to look these over. For number 8, you want to look at these pairs of atoms here. We've got 10 different pairs, and we want to identify, is this an ionic bond that would form? Is this a covalent, polar covalent, or a non-polar covalent bond that would form? And for anything that would be polar, covalent, or ionic, where there's going to be some negative and positive differences there, indicate which end is going to be more positive or more negative. So try this out, see how it goes, and as far as defining bonds as being polar, non-polar, or ionic,